Hello, and welcome to tutorial number 35 of our series. This time I'm in my summer house, so this is going to be a weird camera angle and the backdrop is kind of strange, but that doesn't matter. All that matters is Grasshopper. And this time around we're going to look into a plugin that's called tOpos. That's a topology optimization plugin, and you can get it from Food4Rhino as per usual, as per every plugin that I show here on this channel. And the reason why we are using tOpos today instead of Millipede is that tOpos is a much faster version of Millipede when it comes down to topological optimization. So during our previous tutorial, tutorial number 34, I showed you what Millipede can do with 3D topological optimization. And this time around, I'm just going to show you an alternative, which is tOpos right here. So let's do something very simple. I will just create a box, and I'll just say that's, let's say, 10 by 10 by 10, whatever. It doesn't need to be 10 by 10. Actually, let's do it like that. Some sort of a box, right? And I'll reference it in as a brep. Right here. So now it lives in our Grasshopper window. And now in tOpos, I have a, it's basically like a default setup every time when you do topological optimization. With tOpos, you do the same setup. First of all, we need to create a model. And I don't know if it happens to you guys as well, but when I place the model tool or the model creation icon, it takes a while. It takes like 6 seconds to initiate. I don't know, maybe it's just me. And also you can see here, so first of all, what does this do? And also let me do full names and icons as suggested from the viewers. So this guy basically takes all of the different components or parts that are necessary for topological optimization, and it merges them all into one single model. So it's not a 3D model, but it's a collection of objects, let's say it like that, collection of parts. So what are those parts? Well, boundary domain. So it's basically what kind of boundary. Well, actually, show selected. This guy is kind of boring, right? Let's do something funkier. Let's do a donut. Yeah, something like that. So that's going to be our boundary domain, right? And I can just connect it like so. Oh, or maybe I can't. Wait. Let's see in the model creation tab, what do you have? Boundary conditions, boundary domain. I do need to create this boundary domain node right here for this to work. Yes. So boundary domain, of course, connects to boundary domain right here. And now let's see what it asks. It asks for a mesh, and I have a brep, but I think it's going to be happy about it. I think it's going to internally change it to a mesh. Then density value, Young modulus, and Poisson number. So Young modulus and Poisson number are actual, real values that are used for materials. I believe Young modulus is the elasticity, and Poisson value, Poisson number, I don't remember. But Young modulus is the elasticity. So if I remember correctly, aluminum or maybe steel was 30. I said 30 and wrote 40. It had 30 as a Young modulus, and it had 0.3 as Poisson number. That's why I remember these two numbers, because 30 and 0.3. And of course, every material has a different one. So here, I believe this is steel, so we're dealing with this as if this donut was made out of steel. Okay, so boundary domain is happy now. Let's see what boundary condition wants us. So it wants us to give it a boundary condition, okay. we do have this input right here, or not an input, this node right here, boundary conditions. Okay, so I'll just place it there, connect it, and let's see what it asks. It asks for loads and it asks for supports. Okay, I do have these 4 options for loads here, and I'll just use volume load, but I don't see any options for supports from here. So my assumption is that here I can just directly reference in the brep like that, while here I do need to first for loads, I do first need to create this kind of a volume load node and then reference a brep here. And for load vector, I need to specify the direction. So it's Z, that it's negative, so that it kind of is going to push down, and that its strength is, I don't know, 1, whatever. We don't really care. 1, sure. I believe this is in kilonewtons. Yes, kilonewton for every cubed meter. I have no reference. I have no idea what that, is that a lot? 1 kilonewton is 100 kilograms, almost. 980 kilograms. So it's like 98 kilograms. So it's okay for a cubic meter. We'll figure it out. Doesn't matter. Okay, let's just set it up first. So load mesh. Which parts of this donut are going to be loaded? So I'm just going to kind of, come on, just let me create I'll just create a box here, whatever, and just reference it in. Set 1 brep. Hide the box. So this area where donut and the box intersect is going to be the area which gets loaded with stress. Those points are going to be pushed down. And then let me create another box right here. Push it down. And this is going to be an area where, or rather, let me make it a bit bigger. This is going to be an area where they get supported. So set 1 brep, this guy right here, hide. Okay, so now we have the setup done, right? Supported area, loaded area, and the volume itself. Okay, let me, actually I'll keep the preview for now, that's fine. Let's see what else we have here. We have boundary properties, which we don't really care about, and we have model resolution, which we really care about. So model resolution, you can grab a resolution from here, and model resolution basically states what's the cell size for calculating. So this right here works in units, right? So if I were to write 1, that would mean my resolution is like this pixel right here, or not pixel, but grid cell right here. So I think let's try 1 for now. We perhaps will try, we'll do 0.5 later on, but for now let's try 1. Okay, and immediately you can see, or maybe you can't, depends on your screen, but you can see arrows sticking downwards here in this area, and these kind of crosses showing that it's locked here in the bottom. Okay, so that means we have a model that's working. One more thing about model, if you don't have a GTX card or RTX, if you don't have an NVIDIA card, then you will need to use CPU mode rather than GPU mode. So you just right click on the model icon right here and choose CPU, meaning that then your processor will handle it. This computer right here, this laptop, has a NVIDIA card, so I will be using GPU mode, which is much, much faster. Okay, so now we have the model. Let's go to solvers, and the solver that we will use is called Optimus. Optimus short for optimization, get it? It asks us for a model, so I just connect model to model. It asks us for analyzer parameters. And it says input is optional. If nothing is supplied, default parameters will be used. Sure. This one is also optional. Threshold, doesn't matter. Okay, I will for now input as little amount of inputs as possible, just so that it's easier to follow along, right? So all we need for this one is basically two inputs. A button for resetting and a toggle for running. That's all we need. And then for me, I'm not sure about you guys, but actually let me, why are you doing this? For me, with this pre-assembly solver, with AutoSolver selected, it sometimes lags out, so I always just select pre-assemble solver by right-clicking on the Optimus icon and choosing pre-assemble solver, like that. Okay, we reset, and then this output right here will give us an optimized model once all of this calculates, right? So we need to wait for calculation to, well, we need to start the calculation and wait for it to finish, but that's kind of boring. So instead what I want to do is I want to choose, an output is going to be the model. So I believe if we choose model data and we choose principal stress, maybe. What is that? That is just points. Okay, that is boring. Wait, let me, just a second. That's the loads, that's boring. Element node data. Oh, we already checked node data, right? Yeah, we did. And then we have element data here. Also points, that's, all of those are boring. Okay, so let's do principal stress then. That's going to be more interesting. And let me hide everything except the final output here, just to see better. So of course now it doesn't show anything, right? If I reset it, still nothing. Why is it nothing? Doesn't matter. I will right click on this node right here, Optimus node, and I'll choose to have live preview rather than final preview, so that every step of optimization shows up. So I choose live preview. And one more thing is, if I go to model data, well, for now let's see the principal stress, right? So reset, and I'll just run it. Yeah, okay, so it shows up. And whew, that was fast, it already calculated. So it's not much, right? It's just a bunch of crosses flying about, but that's fine. Instead of this one, I can show you voxel mesh, which is going to be a bit nicer. Oh, but for this one we need threshold, so I'll just say 0.5. Something like that. So the smaller the number, the more of a donut it's going to be. The larger the number, it's going to just leave the voxels that are definitely necessary for the structure. So that's not a lot of voxels. And of course, you can also always do ISO mesh and have the same thing for ISO value. Like that. And get your 3D optimized shape. Okay, so it's definitely not the prettiest, output. So let's keep the voxel mesh output. With that, I'll probably go for something like 0.5 threshold. And let's see some of the settings that we can change. So first things first, analysis, how many steps does it do for analysis and how many steps does it do for optimization? So here we can, I believe it's in solvers, analyzer parameters and Optimus parameters. These two guys, we can just straight up connect analyzer parameters and Optimus parameters to their respective inputs here. Let me make some room. Move these guys away. Okay, these are big ones, right? And here, for basically the way it works, it takes a shape, it analyzes it a bunch of times, and then it says this is the correct output. Then takes that correct output, analyzes that correct output a bunch of times, and then gives you another output, and then takes that output, and so on. So there are like these two loops. One is analyzing, and the other one is optimizing, right? So this is analyzing loops, and it says that every time it's going to do 4,000 passes, 4,000 tests of analysis, and we're happy with it, so we keep it. And this is for every optimization loop, and this is optimization iterations. So here it says it's going to take somewhere between 0 and 20 passes, 20 maximum, which 20 is not a lot. Let me give it 100. And let's just see how it works. So I'm going to reset, run it, and you can see here those voxels are basically like it's just going right through these voxels and trying out different values and so on, analyzing them and just going through iterations, trying to find the most suitable solution. And this is by no means a suitable solution, but because the resolution is so low. But this is, you know, it's better. It's definitely better from what we had before. Okay, so we have that done, and of course I will increase the resolution in just a bit, but a few more things. Volume fraction. This is how much of a volume should be left after the analysis has finished. Right, so here it says 0.2, so that means only 20% of the volume should be left. I will go even more extreme. I will say only 10% should be left. Then you have penalty, change, and sensitivity filter radius. These inputs I will not mess around with. Okay, and the last thing to do here is I will, just to show you how slow it gets, I will decrease the size by half and connect it. So now you can see, you know, much more voxels here appear, of course. And I will just reset the whole thing and run it. And it's going to disappear for a little bit, but now it's starting to, things are starting to emerge. And with more voxels, it can do better optimizations. So let me just quickly check. We are at 0.5 threshold, so I'll just increase the threshold a little bit. Like that, just to see. I believe 0.5 is that the correct threshold to use, but you can always wiggle around that number to get a bigger or a smaller mesh. And here we are just looking at the voxels. Don't worry, we will be looking into the ISO mesh as well. Let's just give it some time. Yeah, it's becoming something for sure. Let's just give it 5 more, 2 more, 1 more. There we go. That's done. Let's look at the ISO mesh, how that one looks like with the same ISO value. Okay. And that's how our optimized ISO mesh looks like within that boundary region, right? So we removed a bunch, but this is what we get. And if I were to show selected, let me just show these two boxes here. That kind of makes sense, right? The way this box is being hugged and this box is here, it definitely makes sense. So that's what we have. And I believe that's like when it comes down to setting everything up, this is all you need. Nothing more, nothing less, only this. So now let's do something a bit more funky. Let me delete the donut. I have this table right here, and if you don't know how to do stuff like this, oh, by the way, this is not the table. This is an input into Grasshopper to generate a table. I have a tutorial on my YouTube, which is called Designing Parametric Furniture or something like that. You'll be able to find it. You just look for an icon with a smooth, cool table, and you'll find it. But basically, I do have a separate tutorial on how to create that kind of design. But now I do have this table, which is a little bit different, and I will reference it in as a brep. Set one brep, there we go. I will create a simple mesh from each face of the brep, so each face becomes a single polygon. And then I will combine and clean the mesh, so it's basically just cleans up the mesh. And let me hide so that this is not in the way. And then I will run Catmull Clark subdivision on it with 2 or 3, doesn't matter, 3, sure, with 3 iterations, like that. And we end up with, you know, this kind of shape. Maybe it's nicer from this angle. Let me show you. Bake, default, okay, like that. Let's take a look at it. Emap. Pretty smooth, pretty nice table. Okay. So again, if you're interested in this, table design tutorial, then just look for that video in my video list. Okay, so we have this mesh right here, which is going to be our new domain mesh. Let me reference it in actually as a mesh, not as a brep, like that, and connect it like so. And now we need the bottom and the top. So just give me a second. All right, so for the top and also for the bottom, I will need to create 2 boxes. I don't think I haven't kept the old boxes that we had, so I will just create 2 new ones. So let me just draw out a box. And why does it, I wonder, why is it snapping to some sort of a, wait, first corner of base, yeah, it is snapping to something. Is it because ortho is on? Yes. Okay, so that was because orthographic projection was on for snapping. Anyway, doesn't matter. We have a box, so I'll just make it a little bit more compact so that it's not in the way. And basically I'll be using this part of the box just to show where the supports are going to be. And let me just do it even more compact, because we definitely don't need it to be over the top. And also I'll just copy it up and make sure that this portion right here is basically where the load is, right, of my shape. And let me just see if everything kind of fits. Seems to be the case. Super. Okay. So we have those 2 boxes kind of modeled out. This is my load box right here. So I'll set that brep here. And this is my support box. I'll set one brep here. Let me just check. This is set to false. That's good, because this is going to be a little bit intense. Set 1. Okay, we have that done. Let me hide the boxes. And let's just see what we have so far. I wonder, will this show? Yeah, this does show the load areas and the support areas right here. Okay, so we have that. perhaps I don't need to see the mesh, or maybe we can do it, let's do it this way. I will custom preview it, and I will say that its color should be white and it should be extremely transparent, just like that. And yeah, no mesh edges whatsoever. Just, you know, something like that. That should be good enough. And this is my voxels right here. So right now it's not optimized, and yeah, these voxels are way too big, as you can probably tell by now. So one way would be for me to change the size of the voxel quite easily by going back here, and where I have my resolution, just changing the size here. But instead what I'm going to do is I will keep it true to scale. So I will say that the resolution is going to be in millimeters, and the resolution is going to be every 10 millimeters. So 1 cubic centimeter resolution, right? Which makes all of this very bad, especially considering that, you know, right now a voxel is basically larger, 1 cube is larger than the shape itself. But that's fine. We will fix it now in this stage, where I will show it like that. We don't need to be accurate, so I'll just measure the distance from here to, doesn't matter, to here. That's 6.9 millimeters. So let's say I want this to be 70 centimeters, which would make this 700. So I just need to scale it up 100 times, right? So I will just select this whole guy, type in scale, 0 around 0.0, and just type in 100. So now this whole thing is a big boy. Yeah, that's nice. Okay, let me hide it now. And this is the resolution that we're dealing with. And you can see, you know, that those boxes are of course sticking out, but that's fine. That's something that we can work around with just in a little bit. For now, I kind of like how this looks. Okay, so we have those boxes, we have the iterations, and calculating those boxes take like 1.6 seconds. Maybe that's fine, just to see how it all works. Yeah, whatever. Let's just say that's fine. So I will reset. Okay, that does take a while. And oh yeah, let's do it this way. I will run this, but I will speed it up, right? So that you guys can see it, you know, being optimized faster. So we have this, perhaps something like that, or maybe I should, let me hide the material display here, turn this to wireframe, and yeah, something like this should be okay. Okay, let's run it. Run. Okay, so this is what we get, and it looks like that with the threshold of 0.7. So now we can mess around with the threshold and kind of get a bit less denser look. But as you can probably expect, you know, you end up getting this branching system here, right? Okay, so now let's see. Yeah, now let's see how, wait, let me just put the phone down there, how it would look like as an ISO mesh, right? So I will go to topos, solvers, not solvers, model data, and I'll extract the ISO mesh here. So that's model and ISO value. I will use the same ISO value, 0.4, like that. Also, while it's calculating, there's the third value that's called deflection, and you can use that third value for calculating how the structure will sag due to load, but we don't really care about it. I might show you deflection later, but definitely not now. So this is how it looks like, and it's not connecting, which is very bad, right? First of all, it means that the ISO value is too low. Second of all, it means that the voxel count is probably a little bit too low as well. So let me try and see how it's gonna look like with 0.2 ISO value. Perhaps it's going to be a little bit more soft. Yes, it is, and we get more branches as well. Nice. So this is what we end up getting. And let's actually see this voxel mesh. Is it an invalid mesh? No, it's not. It's actually a clean mesh. So I might end up using it. But first, let's see how it looks like with the original one here. So there are some issues here and there that needs to be, addressed. If I were to make this full-on, yeah, this is the original one is not the original one, but the new one, the optimized one, is way too thick, right? But that's fine. That's something that we can deal with in a few different ways. For now, I'm happy with the result. And there are a few parts that are just floating about there. So let me do this connect or this joint mesh. So I'll just get rid of all of the small meshes here. So I have the biggest one always in the top of the list and the smaller ones in the bottom of the list. So by using list item, I'll just get the biggest one in the list. So I got rid of all of the small ones. And now I will use smooth mesh tool to smooth it out a bit. And let's say we will do strength of 0.5. So not a lot of strength, but a lot of iterations. So here we have only one iteration. So let's do like 5 iterations of smoothing, and let me hide the original. So this is how it starts looking after 5 iterations of smoothing. We can do better. That's after 10. Certain parts are starting to break down a bit. That's not good. But other than that, it's fine. Okay. And then let's do additional Catmull-Clark subdivision for the mesh. Just like that, to make it a little bit softer. Now let's see how it looks like against the original. So it's still kinda in the way, and also smoothing probably messed it up a bit. How do we deal with that? Okay, usually when you optimize stuff, right, you don't, how do I explain this? Usually when you optimize stuff, you don't just extract the mesh and print it out immediately. You model on top of this mesh that we got here, right? So so this is like me cleaning it up is a really awkward part of the tutorial, because you never do that. You just get that mesh, and most of the time you just get these voxels rather than the mesh, and you just model sets of pipes on top of those voxels, right? So this is a little bit awkward, to say the least. Let's do it this way then. let me delete. So we have the ISO mesh here. Can I do a Boolean sorry, mesh intersection? That is not mesh intersection. Mesh intersection. Can I do a mesh intersection between the original mesh right here and the ISO mesh right here? Yes, we can. Okay. Oh, never mind, we can't. It just crashes. Okay, but what if I use this joint mesh? So I get rid of the mesh, the small meshes with disjoint mesh and list item. Sorry, I'll stop playing in just a second. So what if we just do it with the large mesh? Still crappy. Okay, what if we do it with a cleaned version of it, combine and clean? Still crappy. Okay, we ignore. We don't do that. We don't do that. That is fine. All right. So that didn't work. Well, it did work just as expected, but it doesn't clean up that nicely. To clean it up, you would actually need to model on top of it, and I might do. Let me know in the comments if you want me to do an additional tutorial showing how, when you get this mesh, how you model stuff on top of it to kind of create this optimized geometry. That would be definitely much more of a 3D modeling tutorial rather than Grasshopper tutorial, but that might be interesting to you guys as well. Right now, what I do want to do is, first of all, save this document and save this one, just in case. Then I want to come here and say, actually, my resolution is going to be every 5 millimeters, not every 10, right? So I'm going to use that as my resolution. So in turn, I will end up getting 4 times, wait, 8 times more voxels. And my Grasshopper disappeared. Hello. There we go. There it is. It's alive. No, it's not. It's still not alive. Actually, you can check in Task Manager. You can see just how much memory Rhino is using up so far, right? That's just from the voxels. There we go. So that was 11 gigabytes. And actually I can do, where's my Chrome? Can we do it here? Yeah, that's easier. And task. There we go. So now, okay, we are at 10.5 just from Rhino running NOBS, but that doesn't matter, which is quite interesting. That's it. Basically, what I'm trying to show you is that it eats a lot of RAM when it's calculating this amount of voxels. And now, with this amount of voxels, I will say do, is this off? Yes, it is off. Do not 4,000, but rather 5,000 iterations for every an analysis step. So do 5,000 iterations. Are we going to wait again for like half an hour for this to register? Yeah, I should have, okay. That was my bad, sorry. I should have disconnected the wires before plugging in new parameters. Okay, it's alive. There we go. So 5,000 analysis iterations. And instead of 100 optimization iterations, we will use like 250, something like that. Maybe 300 optimization iterations. So I really want to optimize the shit out of this. But for volume fraction, 0.1 I think is a little bit too optimistic. So we will use like 20% rather than 10% of the original volume. So let us disconnect the, you can see that it takes like half a minute to show those voxels. Let me disconnect the voxel preview for a bit, and I'll just place it next to my ISO mesh. With having it disconnected, I will say 200, or rather, let's go for 300 optimization iterations. I want this to be. Also, it kind of stops optimizing, even if it, doesn't. If it doesn't need 300 iterations to fully optimize something, it will stop at, let's say, 220 iterations if that is all that it needs. And for volume fraction, 0.2. Okay, so 20% of the original volume is still a pretty freaking big volume fraction. So this time, I will not be showing the output, because it's way too, or maybe let's see if principal stress data takes a long time to show. 2.2 seconds, that's not that bad, but it does calculate a lot of shit that we don't care about. Okay, I'll delete it. For now, this is going to be boring, so we're just going to look at this number right here. I'll just hit reset and hit the start button. So now it's loading all of the, yeah, it's done. It was loading all of the voxels into the temporary memory. And now let me speed it up. Actually, I can, since nothing is happening on the left-hand side, I can show you the memory. The memory is kind of boring. CPU is also boring. And for some reason, by the way, Windows doesn't show GPU usage for this particular graphics card. I don't know why. Maybe we don't care. Okay. Let me speed this up, and we will take a look at it once it's done. All right, we are back, and it seems to have actually solved it in 96 iterations, so we didn't even need to do whole 300, which is great. Let us see. I guess let us see what we have. So first I will do something lightweight, which is I will check the principal stress values. So I'll just connect the model to model input here. And that's what we have. And you can already kind of tell, what we are going to be dealing with. Exciting. Anyhow, now let's see. Which one? Let's do this one first. The boxes, right? So I will just take that model and connect it to here. And now we will need to wait a little bit more for the voxels to actually show up. But that will give us a little bit better understanding what kind of value we want to use. So this right here is with 0.4. Like the threshold is 0.4, and in turn ISO value is 0.4, which is, in my opinion, kind of cool, and I actually love it. I think we should keep it. We could go small, bigger or smaller, it doesn't matter, but I think this one looks super. So we will be keeping that. And now this is going to be a very heavy boy. So first of all, I need to say 0.4, like same ISO value. Like that. No drivers, thank you. And now before connecting the model, is there a way for me to... Shit, there's no way for me to save it before, huh? So it's basically, if it crashes, it crashes. Well, YOLO. Let me disable preview of this one, or even disable this one altogether. Disable this one altogether and just connect. And hope for the best. If the previous one, if the voxel preview took half a minute to do, this is going to take longer. This is going to take at least 4 minutes. So I will go and grab some coffee and then we will take a look at this once it's done. There it is. There it is. Oh my god, it's so nice. I love how natural these things look like. So this is what we get, and this is pretty fucking cool. I ain't gonna lie. I really, really enjoy how this looks like, and it's an invalid mesh. Come on, come on. So sometimes it gives us an invalid mesh output. Perhaps combine and clean will help it out. Is it still? Yeah, it's still an invalid mesh. Let's see what can we do to make it work, because I really want this thing to actually work. And it's usually, you know, a few vertices here and there that are shitty. Okay, how do we make this work? Okay, first of all, this joint mesh, let's separate it. Empty mesh parameter. Okay, so it doesn't separate because it's an invalid mesh. Shit. Naked edge, mesh evaluation, mesh attributes. Can I deconstruct the mesh if it's bad? Yes, I can. Okay. Can I construct it then? Like that. Invalid mesh face encountered. Mesh topology might be corrupt. But it has done it. Okay. Combine and clean. Okay, now it's a valid mesh, so we cleaned it up real nice. We can smooth it out as well. So I'll just do smooth mesh like that. And I will just give it like 3 iterations of smoothing, not too much. Well, maybe more actually. Why does it? I guess that's a lot of vertices to smooth. Oh, oops, that's my bad. We are looking at this guy as well. So now it's a little bit more smoothed out, as you can see. So this is the new one, the smooth version, and this is the original version, right? So of course it's more smoothed out, and I can just bake it out now. Default. Hello? Did you? Oh, you are baked. Ooh. Yes. Okay, so this one is baked, and I will also bake out the original mesh right here. just like that. Make a copy of them, or rather just move them here. Let's go for Arctic view maybe, or let's go for shaded view. So that's how they look like together. And actually, let me hide the big one. And this is the optimized one. Looks wonderful. So how do we do this? Let's take this guy and use offset mesh on it. Offset mesh on this guy, and let's add thickness to him. So I will add, this is going to work like an envelope. So I am going to add, what's the thickness of glass? It's like 5 millimeters, right? So let's do something like, yeah, let's do 5. Solid, both sides. If it's both sides, then it's gonna become a centimeter. Maybe we are fine with that. Let's just see if we offset it inside by that much, it's going to make a few mistakes. So let's do, instead of 5, let's do 3. This should be good enough, so it doesn't break too much. Delete and put damage, meshes, solid, yeah, just hit offset. No, that doesn't work. I need this boy to be a bit thicker. So let me do offset, offset mesh, not both sides, only outside. And instead of 3, let's do 7. Hit offset. So it does look fatter now, but now that nice topo mesh is inside of this one, meaning that we can go to Arctic view, for instance, and say that this is glass, and that one, the one that's inside is not glass, it's steel, or something like that. So I will go to material. Not default, I will create a new one and I will say glass. And let me just add a color real fast so that it... can we do gold? Yeah, sure. And the background is really obnoxious, so let me change the background real fast. Like that. And let's choose that mesh and change its material to metal. Use new material, metal. And can we change the color? Yes, we can. And I will just go for stainless steel, whatever, stainless steel. And we end up with something like this. Is there a way to, wait, zoom selected, turntable? Yes, there is. I don't like the glass. Why does glass look so bad in Rhino? Let's go for plastic then, and just say it's hella transparent, but it's also quite frosted. Oh, it doesn't care. Well, whatever. This looks better. So we end up having this kind of a design. That's it. That is it for today. This file, together with the Rhino file, the Grasshopper file, is going to be available for my Patreons. So check out the link in the video description if you are lazy and you just want to download the design. and want to download this mesh and kind of play around with it, or you can just follow along with the tutorial and build it by yourself. Other than that, I will see you in a few days with a new tutorial, and now I'm going to render this bad boy out in high resolution. See ya!